micronutrient deficiencies, also known as hidden hunger, affect over 2 billion people around the world. This happens not from lack of food, but from a lack of vitamins and micronutrients, even in diets that seem sufficient in calories. Surprisingly, seeds are the basis of much of our diet. They are rich in energy, but often poor in essential vitamins like provitamin A, folate, and vitamin E. Our project addresses this gap through a novel approach to nutritional biofortification, without the introduction of foreign genes. We are using an approach that aims to unlock the natural potential of seeds by identifying short DNA switches, regulatory elements and promoter regions of native vitamin genes. These act like molecular on-off switches to activate dormant pathways that already exist within the genome. However, we need to identify which regulatory switches allow for expression within the seed. For this, we are using machine learning to predict these DNA switches, trained on large-scale data from plant genomes. As a visible proof of concept, we are using a Ruby reporter system. When a DNA switch is added to the native promoter and successfully activates the target gene, it produces red pigment in the seed. We can see this activation in real time. We're currently testing this in Arabidopsis, a model plant widely used in research. This strategy will provide targets for minimal and precise genome editing to native regulatory DNA. By doing so, we can create next-generation biofortified crops, nutrient-dense, sustainable, and genetically precise, tackling hidden hunger from within the seed itself.